It might not.
It might not.
All right. One of the things you learn in statistics is to put LY behind everything. It'll probably rain today. All right. So today we're going to start learning rules for differentiation. I missed it. Dadgummit.
That's good.
So the derivative of a constant function is 0, which makes sense. If you think about the graph of a constant function. Yes, Lord? Oh, yes, he's saying get on with it. If you look at the graph of a constant function.
That's a joke.
I was laughing because she was laughing. What kind of a graph is a constant function?
Horizontal?
Yes, it is a horizontal line. So its slope is 0. So it makes sense that the derivative of a constant function is 0. Now, for those of you who are taking AP Physics, is that everybody?
Yes.
Okay, you've already learned the power rule.
Yes.
But you haven't learned why it works.
Oh my god.
What if we don't want to know why?
Well, I'm going to show you briefly why. There it is.
There's a lot of math.
That's great.
There's a
It's good to know.
ellipses.
Pardon?
There's ellipses because there's so many terms.
Yes. So let me show you a slightly faster way to kind of think about it. You guys at some point or another, most of you at least, have seen Pascal's triangle?
Yes.
Looks like this. 1, 1, 1, 1, 2, 1, 1, 3, 3,
It's on the board
1.
behind you if you don't want to.
Yeah.
Okay.
I was playing with it and I decided I needed to have it on here in case anyone wanted to watch this later.
Is that like an
'Cause-
impulse?
Yeah.
Okay.
So notice that for when you're squaring x plus h, like if you have x plus h squared, the second term's coefficient is going to be 2. And when you're cubing it, the coefficient is going to be 3. And if you raise it to the 4th power, the coefficient is 4, et cetera, et cetera, et cetera. So notice that that is always equal to whatever the power was. And then what's going to happen is the x to the nth is going to subtract out because you're going to have a positive 1 and a negative 1. And every other term is going to have multiple h's in it so that when you divide, only this term matters. The rest of them have h's in them, and when h goes to 0, they will all go to 0. So this is why you end up with n times x to the n minus 1. That is the power rule for I guess power functions. Okay? X raised to a power. So, for example, what's the derivative of x to the 7th?
7x to the 6.
Right.
7x6.
7x to the 6th power. Now imagine being required to do that using the definition.
We had to do that on our homework. It was like x squared.
Yeah.
Well, x squared is not exactly difficult, but x to the 7th?
Oh, yeah.
Even using Pascal's triangle, you may have to turn your paper sideways to get it all on there. Okay? So now, I don't know if you guys have learned this in AP Physics or not. The constant multiple rule. Nope? Okay. So if u is a differentiable function of x, and here I usually insert a joke about not being at Westfield and being able to say u is without being looked at strangely, and c is a constant, then the derivative of c times u is c times the derivative of u with respect to x. In other words, if you're multiplying by a constant, you just keep the constant and then take the derivative of whatever comes behind it. Okay? And if you think about it, when you multiply an expression times a constant, you stretch it vertically that many times, right? So it would make sense that the slope would be that many times greater. Okay? So the derivative of 5x to the fourth is 5 times the derivative with respect to x of x to the fourth. So it'd be 5 times 4x cubed is 20x cubed. Now, in practice, nobody writes all those steps out, nor do I expect you to, but I do expect you to understand the constant multiple rule. Page 2. The sum and difference rule. If u and v are both differentiable functions of x, then the derivative of u plus or minus v is the derivative of u with respect to x plus or minus the derivative of v with respect to x. That lets you do polynomials, for example. We'll do other things, but that's the first thing that we'll do is a polynomial. So if we're taking the derivative of this polynomial function, we just do it term by term. Some people call it term by term differentiation. Okay, you're just taking the derivative of each individual term. So dv dt, which is the derivative of v with respect to t, the derivative of t cubed is going to be 3t squared minus the derivative of 4t squared is 8t minus the derivative of 2/3 t is 2/3 plus what's the derivative of 5? 0. Done. Okay, notice there's two different rules about constants. The derivative of a constant is 0. If you have a constant multiple, you keep that constant and then multiply it times the derivative. All right, so let's take a look at this one. Here's an interesting application. At what points do horizontal tangents occur for the graph of bleh? It's pretty horrible looking. Let's see if we can do something with it. To have a horizontal tangent, what's the slope of a horizontal line? 0. So we want y prime, the derivative, which is going to be, what's this first term's derivative going to be?
0.6x cubed.
Try again?
0.8x.
0.8x cubed
I can multiply.
minus, what's the next one?
2.1x squared.
Right? Minus
4x.
4x plus 5. We want that to be equal to 0.
Ooh.
Now, that's a cubic function. Although we have a quadratic formula, there is no cubic formula. So something like this is something that we would expect you to be able to use your calculator for. One of the things you're supposed to be able to do on a calculator is solve something like this. There are several ways to do it.
Graph it.
I think graphing is probably the easiest way.
Okay.
I didn't know it was even supposed to rain today, and here it is about to rain for the second time.
What?
It rained earlier?
Oh, yeah.
Oh, yeah.
I remember thinking, well, it's a good thing that didn't happen during chapel.
Yeah, it was right after the whole sprinkle.
Uh-oh.
Well, so what does it mean when they say that there's a 30% chance of rain?
We're in Calc, not stat.
Okay. So we'll graph this, and I'll do it in a standard viewing window. By the way, going back to a little bit of algebra, what's the most number of zeros that this could have? 3, because this is a cubic function. What is the least number of zeros that it can have?
1.
It's got to have at least 1.
Oh, yeah.
Okay? All right. So we can real quickly go, all right, I want to find the zeros. So second, calculate, find the zeros. This first one is in between -1 and -4. So I'm going to go from -4. I don't know if you guys do this, but I can't stand to just hit the arrows to move it over to the right place.
I do that.
There are times when that just doesn't work real well. And I almost never guess either. I just hit enter again. So x equals -1.862 repeating. Oh, and notice it asked me for the points, didn't it? So that means we should probably give both the x-coordinate and the y-coordinate. All right, so here's what I'm going to do. I'm going to quit out of this. And I want the y-coordinate for this. So what I'm going to do, remember that your calculator still has that x value in its head. So if I go 0.2 x raised to the 4th minus 0.7 x to the 3rd minus 2x squared plus 5x plus 3. It'll crank out the y value. And remember that you can round things, your final answers, you can round them off to 3 decimal places, or you can truncate after 3 decimal places. So our first point is -1.862, comma, -8.488. The cool thing about this is that when I go back to my graph, so I want to graph that again. When I go to the 0, I do second calc, find the 0. The second one looks like it's somewhere between 1 and 2. I'll guess between 0 and 2. Nope, I hit enter one too many times. Try that again, between 0 and 2. So the second one is at 0.948. And if I quit out of this and just go back to this, I don't have to type that all in again. I can just do second, enter, bada boom, bada bing. So although calculator mastery doesn't really come into the AP exam, being smart about when to use your calculator and how to use your calculator does. And then we'll do it one last time for the last one, which is between 3 and 4. Find the 0. It's somewhere between 3 and 4. Man, 3.538. And again, to get the y-coordinate, I don't have to type all that in again. I can just do second enter, and it gives me that point, -32.238. Okay, any questions about that? We could, if we wanted to, graph. You can always kind of check it by graphing. Dang. I saw that one.
Yeah.
You could graph this original one and look to see, does it have horizontal tangents at approximately these points? Let's go ahead and do it. I'm a little worried that we're about to, lose power or something, but that's all right. I could just continue on the whiteboard.
Kind of long. But it doesn't.
It's not that bad.
30 minutes. You can probably do it in less than 30 minutes.
Something doesn't seem right. So I'm going to trace this to negative 1.862. Did I type something wrong?
Yes, you put the function wrong.
I typed it wrong?
Yeah, the function.
What did I type?
Type a different function.
What did he
What? No, I think you typed it right.
He typed it right in the graph, but
I mean, it's 4x plus 5, right?
oh, you did 0.02.
Oh,
Exactly.
I tried to do 0.2. Well, that would explain why these are all so far off. What? Is Lily being mean?
I'm not being mean.
She would never.
At least the nicest person I know, actually.
Aw.
You don't know very many
I
people,
love
do
that.
you? All right, sorry about that. All right, moving on. Now, although you can add and subtract derivatives, if you have a product, you can't do one derivative times the derivative of the other and expect to get the right answer. Well, think about it this way. If I had x times x squared, right? That's x cubed. The derivative of x cubed we know is 3x squared. But the derivative of x is 1, and the derivative of x squared is 2x, and if I multiply them together, I don't get anywhere close to 3x squared. Okay? So what we have is something called the product rule, which says that if u and v are differentiable functions of x, the derivative of u times v is u times the derivative of v with respect to x plus v times the derivative of u with respect to x. So in each case, you're going to keep one and multiply by the other, the derivative of the other. So keep one, derivative of the other, then switch. And because it's plus, it really doesn't matter which one you do first. I almost always, just as a matter of habit, keep the first factor times the derivative of the second factor, but that's not important. All right, so let's verify the product rule by finding the derivative of this thing two different ways. First, by multiplying out the expression and then differentiating, and then by using the product rule. So if we're multiplying this out, f of x is going to be equal to x to the fifth plus x cubed plus 3x squared plus 3. Did I get all the right terms this time? So then f prime of x is 5x to the fourth plus 3x squared plus 6x. Now let's do it by the product rule. So f prime of x will be, I'm going to keep the first factor, x squared plus 1, times the derivative of the second factor, 3x squared, plus the second factor times the derivative of the first factor, which will just be 2x. So that's 3x to the fourth plus 3x squared plus 2x to the fourth plus 6x is 5x to the fourth plus 3x squared plus 6x. QED. I knew that would make you guys do that.
Oh,
Yes?
where is that? The prime formula?
I'm using the product rule. The product rule says keep the first, then take the derivative of the second, and then reverse, plus keep the second times the derivative of the first. Okay? Now, is there any reason to do this on a polynomial? No. You should simplify the polynomial first, then take the derivative. Now, we're going to get to some where it's like sine times 4x cubed, and you can't do that. You have to use the product rule. Okay? But if you can simplify an expression before you take the derivative, do it. Okay? That's kind of a big deal. Students frequently make life way harder on themselves by not simplifying first. All right. Last thing, the quotient rule. So the quotient rule says that if u and v are differentiable functions of x, then the derivative of u divided by v is, you must start with the denominator, v, times the derivative of u with respect to x, minus, not plus this time, u times the derivative of v with respect to x, all over v squared, provided that v is not equal to 0. And there are all kinds of little mnemonic devices. You don't need to write this down, but some people will write it as high over low, and then it's low d high minus high d low.
Are you nothing?
Pardon?
Like for real?
Yeah, people will remember it this way. Over, and if you want to make it all rhyme, you say low d high minus high d low over the square of what's below.
Do it again.
Or you can do high ho, where it becomes high over ho. It's ho d high over high d ho over ho ho. Whatever it takes to help you remember it. All right, so let's find the derivative of this and support that graphically. So f prime of x. By the way, there is a case to be made of, well, maybe I should do long division on this and simplify it first, but we're not going to. So the denominator first, x squared plus 1, times the derivative of the numerator, 2x, minus the numerator, x squared minus 1, times the derivative of the denominator, which is also 2x, all over x squared plus 1 quantity squared. If this was a free response question, and by the way, it won't be, you won't get a free response question like this on the AP exam. You get a multiple choice question because they want you to simplify it. So we'll distribute, that'll be 2x cubed plus 2x minus 2x cubed plus 2x over x squared plus 1 quantity squared. The 2x cubes are going to add out, and I get 4x over x squared plus 1 quantity squared. How do we support that graphically? Well, we're going to use inderiv to take the derivative of this on our grapher and also graph this and see if they're really the same graph. So let's do that. So clear that out. So I want 4x over the quantity x squared plus 1 squared. And I want to compare that to the numeric derivative. So that's math 8, the derivative with respect to x of x squared minus 1 over x squared plus 1 evaluated at x. And so that we can see it, I'm going to come all the way over here and hit enter 4 times so that it's a little bouncing ball. And now let's graph this thing. So there was the derivative the easy way, and notice it takes it a lot longer to do it the hard way, but you notice it traces it exactly. Pretty good indicator that we did well. Okay? All right.